When you hear words like open, proprietary, and modular in security engineering, it can sound like a debate about brands or personal preferences, but the real issue is much more practical and much more important. These design concepts shape how a system is built, how it changes over time, and how confidently you can defend its security under pressure. A beginner might think the safest choice is whichever option sounds most secure in marketing language. Yet security outcomes usually depend on how well the design fits the mission, the constraints, and the realities of maintenance and assurance. The exam often pushes you to think beyond labels and to reason about trade-offs like visibility, control, independence, complexity, and evidence. If you learn to choose among open, proprietary, and modular approaches as engineering decisions, you can explain why one fits a scenario better than another without needing to memorize product details. That is the goal here, to build a clear mental model of what each concept really means, where it helps, where it can fail, and how to choose defensibly. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A strong foundation starts with plain language definitions that stay stable even when technology changes. Open design, in this context, refers to designs and implementations where interfaces, behaviors, or source code may be visible for review, and where the security claim is not based on hiding how the system works. Proprietary design refers to designs and implementations controlled by a single vendor or organization, where internal details may be restricted and where users rely on the vendor's decisions, processes, and assurances. Modular design refers to building a system from separate components with defined interfaces so that parts can be swapped, updated, or isolated without rebuilding everything. These are not mutually exclusive because a system can be modular and still use proprietary components, and it can use open components within a controlled architecture. What matters is how each concept affects trust and risk. When you see these terms in a scenario, the question is rarely about ideology. It is about how these choices change attack surface, change management, integration risk, and your ability to produce evidence. To connect these concepts to security outcomes, it helps to remember what security engineering is really trying to accomplish in a system. Security engineering aims to make the system behave predictably under both normal conditions and stressful conditions, including misuse, failures, and attacks. Predictable behavior requires clear boundaries, controlled privileges, and a way to verify what the system is doing rather than guessing. Design choices influence predictability because they influence how complicated the system becomes, how many assumptions exist, and how many parties must coordinate to keep it safe. A beginner mistake is to treat openness as automatically safer or proprietary as automatically safer, but neither is a guarantee. Open components can be poorly maintained or integrated carelessly, and proprietary components can be well engineered or badly engineered, depending on the vendor's discipline. Modular design can reduce blast radius by isolating parts, but it can also create interface complexity that introduces new vulnerabilities. Your job is to reason about which choice creates the most defensible path to security given the scenario. Open approaches often appeal to security engineers because they support inspection, learning, and verification, which are core to assurance. When something is open to review, more people can examine it, which can lead to faster discovery of defects and more confidence in how it behaves. Openness can also reduce reliance on marketing claims, because you can evaluate evidence, such as code quality, design clarity, and the maturity of change practices. For beginners, it is important to avoid the misunderstanding that open automatically means secure, because openness is not a control, it is an opportunity for scrutiny. If no one actually reviews the system, or if your organization lacks the skill to evaluate it, openness may not translate into better outcomes. Open solutions can also create a responsibility shift, meaning you may need to manage updates, dependencies, and integration choices more actively. In exam scenarios, open options often shine when transparency, auditability, and the ability to validate claims matter, especially in environments that value evidence and independent review. At the same time, open approaches can introduce predictable failure modes if they are adopted without discipline. One failure mode is dependency sprawl, where a system quietly relies on many small components and libraries, each with its own update cycle and risk profile. Another failure mode is false confidence, where people assume community review has happened thoroughly when, in reality, the most critical parts may have very few reviewers. A third failure mode is delayed patching, where vulnerabilities are known publicly, but the organization does not have a reliable process to evaluate and apply updates quickly. These are not arguments against open design. They are reminders that security outcomes depend on lifecycle management and accountability. If an organization chooses open components, it must treat maintenance and monitoring as part of the design decision, not as an afterthought. In exam thinking, the stronger answer is often the one that recognizes both benefits and obligations, showing that openness supports assurance only when paired with disciplined configuration management and timely updates. Proprietary approaches often appeal to organizations because they promise support, consistency, and a single accountable party, which can be valuable when a system must operate reliably at scale. In a proprietary model, a vendor might provide integrated components, tested combinations, and controlled update mechanisms, which can reduce integration uncertainty. Proprietary design can also simplify procurement, training, and troubleshooting because the environment is more standardized. For beginners, a key misunderstanding is to equate proprietary with secret and secret with secure, as if hidden details prevent attackers from learning how things work. In reality, attackers can often learn behaviors through observation, and security that depends on secrecy tends to be fragile. The real security strength of a good proprietary approach comes from engineering discipline, quality assurance, and strong update and vulnerability response practices. In exam scenarios, proprietary options can be strong when the organization lacks the capacity to maintain complex dependencies and needs a reliable support structure, but only if the choice is paired with evidence expectations and governance. Proprietary approaches also have predictable failure modes that show up in security engineering decisions. Vendor lock-in is one, where the organization becomes dependent on a single vendor's roadmap and cannot easily pivot if risk changes or new requirements emerge. Limited visibility is another, where the organization cannot easily inspect internal behaviors, making it harder to validate security claims and harder to investigate incidents deeply. A third failure mode is delayed or constrained patching, not because patches never come, but because they come on the vendor's schedule, and the organization may have limited options if the vendor prioritizes other customers or other features. There is also the risk of overtrust, where teams assume the vendor's reputation guarantees security and therefore relax internal controls like monitoring, configuration baselines, and access governance. In exam reasoning, a strong response recognizes that proprietary can be a valid choice, but it must be managed with contractual expectations, internal verification where possible, and plans for continuity if the vendor's support changes. Proprietary design is not a free pass. It is a trade that shifts certain responsibilities and risks. Modular design is often the most powerful concept for secure outcomes because it directly affects how damage spreads and how changes can be managed. A modular system is built from components with clear interfaces so that each part has a defined responsibility, and the system can evolve without every change rippling everywhere. From a security standpoint, modularity can support isolation, meaning a compromise in one module is less likely to grant access to everything. It can also support least privilege because each module can be given narrow permissions rather than broad system-wide access. Modular thinking aligns with trust boundaries, because modules often represent boundaries where data and commands cross and therefore need validation and authorization checks. Beginners sometimes think modular design is mainly about convenience for developers, but for security engineering it is about controlling complexity and enabling assurance. In exam scenarios, modular approaches are often preferred when the system must change frequently, integrate with multiple partners, or maintain high confidence over time through clear boundaries and traceable interfaces. However, modular design can also create security risks if the interfaces between modules are not treated as first-class security concerns. Every interface is a boundary, and boundaries are places where assumptions can be exploited, such as trusting input formats, trusting identity assertions, or trusting that a caller is authorized. A predictable modular failure mode is building many modules quickly and then connecting them with weak assumptions, which creates a system that is modular in name but tangled in practice. Another failure mode is inconsistent security enforcement, where one module validates input carefully while another assumes validation already happened. A third failure mode is complexity in identity and authorization, where services call other services and permissions become difficult to reason about, leading to overprivileged service accounts. Modular systems also require disciplined observability and monitoring, because tracing actions across modules can be challenging without good logging and correlation. In exam thinking, modularity is strongest when it comes with consistent interface contracts, clear authorization models, and evidence-producing monitoring, because those elements keep modular complexity from turning into hidden risk. Choosing among open, proprietary, and modular options becomes easier when you focus on security outcomes you must produce rather than on abstract preferences. If the scenario emphasizes independent verification and strong auditability, open elements can support those needs by enabling scrutiny and evidence gathering, especially when assurance is important. If the scenario emphasizes operational stability with limited internal capacity to manage complex dependencies, a proprietary approach might reduce integration risk, provided you can still demand evidence and maintain oversight. If the scenario emphasizes change, integration, and limiting blast radius, modular design often becomes central because it helps you isolate functions and manage evolution. The best answers usually avoid extreme claims like always choose open or always choose proprietary, because security engineering is about context-driven decisions. You want to show that you understand what the design choice changes in terms of trust, control placement, maintenance workload, and assurance confidence. When you can explain that chain of effects, your decision becomes defensible, which is what the exam often rewards. A practical way to reason is to think about who controls change, because change is where security tends to drift. In an open approach, you may have more control and more flexibility, but you also carry more responsibility for tracking updates, evaluating risk, and applying patches in a timely way. In a proprietary approach, the vendor controls much of the change, which can reduce your workload, but can also reduce your ability to respond quickly when your risk environment changes. In a modular approach, you can often change one module without rewriting everything, but the interfaces and dependencies must be managed carefully to prevent integration vulnerabilities. A beginner might focus on the initial build, but security engineering cares deeply about the next year of updates, migrations, and new requirements. Exam scenarios often include hints about change pressure, such as rapid delivery cycles, frequent feature requests, or evolving threat environments. Strong answers align the design concept with the organization's ability to manage change without losing control of security posture. Another important lens is evidence and assurance, because some choices make it easier to produce justified confidence. If you cannot observe how a component behaves, or you cannot validate that controls are working, you may end up relying on assumptions rather than evidence. Open designs can support evidence by enabling review and understanding, but only if you have processes to turn visibility into verification. Proprietary designs may provide vendor attestation and support artifacts, but you must still evaluate whether those artifacts meet your assurance needs and whether you can confirm behavior in your environment. Modular designs can support assurance by allowing you to test and validate components and interfaces in a controlled way, but distributed behavior can complicate evidence collection unless monitoring is designed in. Beginners sometimes treat assurance as paperwork, but assurance is really about confidence that stands up under questioning. On the exam, when a scenario asks about meeting requirements or demonstrating control effectiveness, the best design choice is often the one that makes evidence practical and reliable over time. It is also valuable to connect these design choices to attack surface, because design influences how many pathways exist for misuse. Open or proprietary is not, by itself, a measure of attack surface, because attack surface depends on exposed interfaces, complexity, and unnecessary features. Modular design can reduce attack surface if it allows you to separate and minimize exposed functions, but it can also increase the number of interfaces if the architecture is overly fragmented. Proprietary integrated systems may reduce interface complexity, but they might expose large shared management surfaces that become high-value targets if not protected carefully. Open systems may provide more transparency into what is running, which can help reduce unnecessary components. But they may also bring in many dependencies that expand surface area if not managed. In exam scenarios, look for cues like external integrations, remote access needs, and shared administrative control because those cues often point to where attack surface matters most. A strong answer shows you can balance functionality and exposure, choosing a design concept that supports reduction of unnecessary pathways. The human side of the decision also matters, because security engineering choices must fit the organization's skills and governance realities. A modular system with many open components can be secure, but only if the organization can manage updates, review changes, monitor behavior, and respond to issues consistently. A proprietary system can be secure, but only if the organization avoids blind trust, maintains strong configuration management, and demands timely vulnerability response. In both cases, clear roles and accountability are necessary because security posture is not maintained by technology alone. Beginners sometimes assume the best technical choice always wins, but a technically elegant choice can fail if it cannot be operated and assured. Exam questions often embed organizational constraints, like limited staffing, strict compliance requirements, or high availability needs, and those constraints change what is realistic. Security engineering is not about ideal designs in a vacuum. It is about secure outcomes in real environments with real limitations. Showing that you can match the design approach to operational capability is a sign of mature reasoning. As you develop comfort with these concepts, it helps to think in terms of combining them intentionally rather than treating them as exclusive options. A system might use modular architecture to isolate critical functions, use open components where transparency and auditability matter, and use proprietary components where integrated support and controlled behavior reduce risk. The security engineering challenge is not to pick a label and stop thinking, but to decide where openness helps, where vendor control helps, and where modular boundaries help, and then to ensure the interfaces among those choices remain secure. In practice, the safest outcomes often come from designing clear boundaries, minimizing unnecessary trust, and ensuring that the chosen components can be monitored and updated with discipline. Exam scenarios sometimes reward hybrid thinking because real systems are rarely pure examples of a single model. When you show you understand how to balance transparency, supportability, and isolation, you demonstrate that you are reasoning like an engineer rather than repeating slogans. As we close, the central skill is being able to choose open, proprietary, and modular design concepts based on how they affect control, evidence, and change, because those are the engines of secure outcomes over time. Open approaches can strengthen assurance through transparency and review, but they demand disciplined maintenance and realistic ownership of dependency risk. Proprietary approaches can improve stability and simplify integration, but they can reduce visibility and create reliance on vendor timelines, so they require governance, clear expectations, and plans for continuity. Modular design can limit blast radius and support least privilege through clear boundaries, but it can also introduce interface complexity that must be secured consistently across modules. When you face a scenario, the defensible path is to identify the mission and constraints, then choose the design concept or combination that best supports secure behavior, manageable evolution, and evidence-backed confidence. If you can explain why your choice reduces predictable failure modes and supports assurance, you will be answering in the way ISSEP expects, with security engineering reasoning that is grounded, contextual, and complete.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.